So today we've got a guest lecturer, Mr. Bear. So in moving through our reactions, we've got our benzylic carbon reactivity. Um, and this, well, if we take a step further back, really what this particular lecture is going to be looking at is all of the kind of weird reactions that can potentially happen around our benzene ring. So one of those kind of sites of reactivity is the benzylic carbon position. And I know that sounds like we're talking about a benzene, but what we're actually referencing is the carbon next to a benzene. That position is known as benzylic. It's very similar to the carbon next to an alkene, which was known as allylic. And the reason that position becomes so kind of special is that if we form, say, a carbocation there, we've got lots of resonance stabilization. And that stabilization goes a long way to making things better or easier or more reactive. And so that's why we would go through and kind of address that. So if we continue on, maybe, for the love of peanuts. Sometimes technology works with us and sometimes it does not. If we were to say, look at the alkyl halide in this case, we would see this reaction happen with a pretty high efficiency and yield and speed because we would be forming a carbocation. Right? How do we know we have a carbocation? So this goes back to our substitution unit back in first semester. We see a tertiary halide. We've got 3 carbons connected. That tertiary substrate supports SN1 mechanisms. We can look at our nucleophile, and we know we have a weak nucleophile because it is uncharged. Both those pieces together suggest the mechanism we're going to be going through is an SN1, so we're going to be forming the benzene, or not benzene ring, but a carbocation. That carbocation is more stable than, or in fact is the most stable carbocation we can get, because we get resonance and we get this tertiary stability. So both those pieces together make that incredibly stable. Water could then come in as our weak nucleophile, react. We would then do an acid-base step to deprotonate and get us to the final alcohol. Okay, so that resonance really contributes stability and allows for that formation of the carbocation. Other potential examples, we could look at it in another kind of substitution. This one we would probably lean towards SN2, and it's less of this resonance issue, but it contributes to a dropping of the activation barrier, okay, for that individual reaction because of the kind of inductive stabilization of the benzene towards the carbon of the halogen is more susceptible to leaving, opens up that backside, and our hydroxide attacks really, really easily. So the benzylic position does have this kind of special chemistry, but that's all technically review. What becomes more interesting is that if we go through and throw in, say, some oxidizing agents like chromic acid is a really strong oxidizer. And it turns out that if we have one benzylic hydrogen present, then that benzylic position gets fully oxidized. So we've got that example reaction shown immediately underneath. Okay. One of the first questions that pops up in my mind is, what the heck happened with the rest of those carbons? Well, as far as you're concerned, we don't care. Okay? So don't stress about those. Your primary focus is that we're going to oxidize the benzylic position, which is this guy, and we're going to fully oxidize it. Not just this menial, I'm just going to remove hydrogens and put oxygens. I'm just going to blast the crap out of it and replace virtually every atom with an oxygen except for the benzene ring. Why except for the benzene ring? Well, it's likely because that benzene ring can contribute some stability towards the acid portion of this, right? So that's probably why we don't immediately lose the ring. If we continue down to that lower example, if we look at that benzoic position again, you might note that they're just carbons here. And so this is where it gets interesting. To start the cascade of this reaction all the way down to benzoic acid, you have to have a benzoic hydrogen. If you don't have one, chromic acid doesn't get a foothold on the structure, and without that foothold, man, the reaction doesn't happen. Okay, so this is a no reaction. Okay, so of course we would now try and scaffold this out and see potentially ways to make it more difficult. So number one, are there other oxidizing agents? Well, yeah, permanganate was another oxidizing agent, and it turns out permanganate will do the same thing. Right? So be kind of aware of that. We do have to be looking at a strong oxidizing agent, and permanganate and chromic acid are both very strong oxidizing agents. So here we go, a whole bunch of carbon side chains. Note here we're throwing in the permanganate, so we should now be able to predict what our products would be. So if we go through and start with our toluene, we've got those 3 hydrogens. That would suggest the toluene should go to benzoic acid. Okay? And indeed it does. We go to the alkyl benzene, right? You might look at that and be like, well, there's no hydrogens. Right? This is why we need to be very cognizant of that material that we learned back in first semester about implied hydrogens and structures, so that we can see that there is a hydrogen there. Okay, that one will also go to benzoic acid. The alkyl benzene also has a hydrogen there. So what will it do? Well, it will also go through and oxidize. Right? Where we're going to encounter potential issues would be the last 2. So the alkynyl, there is no hydrogen there. That would exceed the octet. So we might predict that that doesn't react. Right? It does though, and it's likely due to the presence of those pi bonds that are really causing the chemistry at that position to be exploitable by our oxidizing agent. Okay? And in fact, as I reference that, it's irrelevant, the benzoic position at this point, because what we should remember from Unit 1, that triple bond is susceptible to attack by our permanganate. So that's just a triple bond oxidation reaction. It does oxidative cleavage, splits that puppy open, and we get our oxygens. For that matter, same deal with the alkene. That's just an oxidative cleavage reaction that fully oxidizes, which is what permanganate should do. We move to the acyl benzene, so these 2 are review. We move to the acyl benzene, and that one gets a little bit weird. We don't see any alpha hydrogens, and it doesn't fit the pattern that we saw in Unit 1 when discussing the nonpolar pi bonds for oxidation. All I got for you is that it will oxidize, right? And it is likely due to the presence of the hydroxide being able to come in, nucleophilically attack, form that hydrate, and as soon as we've got that hydrate, we get the a potential for the permanganate to really lock on, and once it's locked on, we're going to be running that full oxidation. So while this slide may make it look like we don't get, or we get a whole bunch of different products, it all boils down to, well, that line was supposed to disappear, that's fine. We get our benzoic acid in all of these cases. Okay? So toluene, or A, B, and E are kind of new. C and D are really just review, because those are just looking at the standard oxidative cleavage. Okay? Nitrobenzenes. So we want to go through and reduce. So we just talked about oxidation around our benzene structure, and really what we're referencing is the substituents on it. Could we go through and reduce a nitrobenzene? Well, first and foremost, we would need a nitrobenzene. Okay? So this is where we could start to take advantage of a little bit of nomenclature. A nitrobenzene is going to be a benzene ring, and then it has to have a nitro on it, an O2. So we've got our nomenclature from the very beginning of this unit now addressed. The next part, what reagent do we need to form the nitrobenzene? This reflects back on the last lecture, which summarized all of our common electrophiles. That's going to be HNO3 in the presence of H2SO4, both of these being concentrated. Right? And that's going to get us our nitrobenzene. What makes this particularly interesting, or not interesting per se, is that what we want to do is reduce it. Well, if we look at the nitro, that nitro position is really oxidized. We've got lots and lots of oxygens on it. So if we want to reduce it, that means remove oxygen and replace with hydrogen. So the reduction that we would be looking for would now be our benzene ring, but now instead of having oxygens, we have hydrogens. Right? So it needs to be a reduction. We've seen some reducing agents before in the past, and they can be used with some efficacy. But really what's going to be more relevant for you is that we will see the introduction of, another reagent. So the H2 and palladium, that's old hat stuff. What we're talking about here is HCl and a metal is ultimately what we're referencing. This is what's known as a dissolved metal reduction. Right? Because we're taking literally iron metal and we are dissolving it in the acid. The process of dissolving it creates an oxidation reaction or a redox reaction that allows for the reduction of the nitro. What makes the HCl and metal a little bit more special is it's a little bit more selective, and we're less inclined to see secondary reactions when using the HCl and the metal. Does it have to be iron? No. Okay. So this is why dissolved metal is potentially a better term to memorize if you're going to go through and memorize this, which I would recommend memorizing this because I'm not showing a mechanism. Remember, it's a dissolved metal. So if you see HCl and the metal, you're doing a nitro reduction. The two most common metals that I've seen are iron and tin, tin being the symbol SN. And I shouldn't have capitalized that in SN. Okay, so both of these go through and work. They will do the reduction. We can call it catalytic hydrogenation or dissolved metal. The catalytic hydrogenation, I know they're referencing here as a new reaction. It's not really a new reaction because we've seen H2 and platinum or palladium in the past. We just haven't seen it being or acting on NO2. That catalytic hydrogenation reduces a whole bunch of different things, and believe it or not, you can adjust the conditions on that to make it more selective, but we don't see those conditions pop up in any of our exams. So don't stress on that. Really what you need to be focusing on is just that H2 and a metal, palladium or platinum, or for that matter nickel, will do a reduction of pretty much anything except the benzene ring. Note the benzene ring is not getting reduced. Right? To do that, we'll have to move on to a different reagent, and we'll see that I think in the last video of the lecture sequence. Right? So now we have our reduction of nitrobenzenes to aromatic amines. This becomes useful to us because if I want to put an amine on the structure, how would I go through and do it? Okay, well, if we look at our standard mechanism for EAS, the aromatic ring is acting as a nucleophile. To get NH2 on there, the most likely place for NH2 would be negative. What are the odds I'm going to be able to get an NH2 positive? Right? That's just slim to none. So if I want to get an NH2 on the structure, usually the best way to go through and do it is to do this nitration reaction followed by a reduction. That sets you up with that amine. That's really the only way you're going to get it on there. And that, of course, is a lie because we'll see that again as another way to do it later in the semester. This one is a bit crazy, right? So I just want you to be aware of that. I think it is a fascinating and cool reaction, but it is definitely a bit out there, and it's probably best to just straight up memorize And by memorize, not even bothering to memorize the mechanism, but really when you see NaNO2, that should be your red flag that whatever you do in step 2, because if you notice, that's calling a step 1, that whatever you're doing in step 2, the negative thing, right, gets put on there. Okay, so we lose the NH2 and we put whatever that negative was on the structure. Right? I don't know what this particular example is, but we'll go ahead and say it was iodine. Right? It's neat. It's interesting because we can get a whole bunch more variability within it, and we'll see that here in just a second. I do want to walk through the mechanism because I do think the mechanism is neat. It's got a lot of stuff going on with it. But before we actually step through the mechanism, I'm going to kind of jump a little bit around. This is where we could use CuBr and we could put a bromine on the structure. For those of you saying, couldn't I have just done benzene straight to with Br2? Yeah, you could have. Right? And the point of this reagent isn't that you're putting bromine on that structure. It's that you have this other piece that's on the structure. That other piece has an effect on how that aromatic ring reacts. That effect will become really important when we move into the next, I think it's the next, in 2 videos, when we start looking at multiple substitutions on an aromatic ring. Because once you put one on, everything changes, and now our reaction becomes potentially a little bit more interesting, or at very least, we've got to look at it a little bit more carefully. Right? So it can be useful because we can get some of the benefits of an NH2, but then replace it with a bromine later on in the game if we really wanted to. So I know this looks big, right? This is what's known as the Sandmeyer reaction, right? And again, I'll walk through the mechanism, but there is a myriad of reagents that we'll go through in that second step to replace. And if you go through and look, in a lot of these cases, Cl, that's negative, bromine, negative, Cn, negative, iodine, negative, fluorine, negative, OH, negative. What the heck? Because it's not H minus, it's H plus. And so that one is a little bit weird. But if we go through and look at the majority of these reactions, what we're putting on the structure is a negative species. Again, that's in and of itself interesting and bizarre because you're putting a negative on a nucleophilic structure. And so that's one of the reasons why the Sandmeyer reaction is potentially named, because we're taking 2 things that theoretically shouldn't react and somehow ending with that product. And that's kind of cool. Right? Here's the mechanism beginning to end, not the Sandmeyer part, but getting up to the important intermediate, which we'll see here in a second. Okay? I just wanted you to see how long it is and that this is what we're going to attempt to draw out. So if we backtrack through this, and actually I'll keep that structure up there. Right? When we're looking at this, what we're saying is that step 1 forms something. This something then reacts with step 2 to continue on. Okay? That thing that it's reacting with, as we said, was typically a minus, which means if we're looking at our something, for sure we know we need a benzene ring because we haven't lost that through this process. And since we're getting a minus there, this carbon needs to somehow become electrophilic, which means whatever's out here needs to be a decent leaving group. Okay? And again, the mechanistic aspect of the second step we don't care about, so don't worry about that one. Right? It is being catalyzed by the copper, and that's one of the things that makes it more complex and just we don't need to worry about. But getting up to this something structure is kind of neat. Right? And I think it goes through some kind of relevant review topics. So let's go ahead and start. We've got our aniline, sodium nitrite, and then HBr. Right? As we've talked about in the past, if you don't know where to start, what you should do would be look for the most reactive thing. Okay? Most students will say, oh, I have nitrogen with a lone pair on that electrons, the aniline, that's what should react. Well, is that the most reactive thing? Okay? No. HBr is a strong acid, which gives us H+. Okay? That's my first focus. I could then say, oh, well, then aniline reacts with that hydrogen. Again, is that the most reactive thing? Take a look at NaNO2, and this one becomes interesting because we get our sodium ion and then NO2 minus. Well, which do you think is more active, a negative charge or a neutral? The negative probably makes more sense, so we should be targeting the NO2 to react with our HBr, not the aniline, okay? At least not yet. Before we push into that reaction, it's useful to go through and actually represent what NO2 minus is. And because I usually bollocks up this Lewis structure, I've actually got to write it all out. Nitrogen comes in with 5, oxygen comes in with 6. Yes. There's 2 oxygens, which gets me 12. The charge means I need to add 1 electron. 12 and 6, 18. I've got nitrogen, oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've got all of my, did I draw all the electrons? Oh, 18. All right, now I've got 18 electrons. The nitrogen does not have its octet, so I'm going to move a pair of electrons from one of the oxygens in to make a double bond. Okay, now that I have the Lewis structure, now I can start to do something as far as reactions. Simple acid-base reaction. We would get Rn. Remember, this was a beastly long one, so I'm probably going to regret having drawn such a long arrow there. Okay. So we might not think that's a big deal. One of the things that kind of helps to push this is that we are in a strong acid environment, and what we could potentially see here is, sorry, that was nonsense, ignore that. We now have kind of this neutral structure, right? So there's the end of it, right? However, remember, we do have a polar pi bond, right? And we have a nucleophile with the aniline. Why is that potentially beneficial? Well, the aniline lone pair electrons could come in and attack and break the pi bond. The result is we'll have our benzene, 2 hydrogens, and we'll have a nitrogen-nitrogen bond. And we've got lots and lots of stuff to draw in here, right? And that nitrogen still has a lone pair because we didn't do anything with that, right? That bottom nitrogen would now be positive. It doesn't want to be positive, so it could dump that hydrogen off to the environment. So we could go through and say we've got a solvent-mediated acid-base reaction. Okay? That would neutralize that positive. Okay? We could have the electrons from our negative come back down, but if they came back down in a nucleophilic addition kind of elimination pattern, we'd end up ejecting the nitrogen, which should take us backwards, and that's not particularly useful. Is there a way that I could foresee this one getting ejected? Well, hydroxide's a bad leaving group. What if we protonated? We're still in a strongly acidic environment. How about those electrons also come in? Right? For the record, what I'm showing is 2 solvent-mediated and reagent-mediated steps in the same step. So what I'm trying to do is condense the amount of steps going on this so we have more space to draw. This is 2 steps, and they should be shown independently. We draw out the reaction, those people being like, well, dang, what did that do for us? Right? Well, we continue to draw out nitrogen, lone pair, H2, positive, oxygen with that negative charge. That negative could now potentially come in and kick out water as a decent leaving group. Right? And you might be like, again, why? Why is this useful? Right? Well, let's look at it a little bit closer still. We still have a polar pi bond. Right? Everything has octets, so we might be like, okay, we're good. Well, the oxygen could have donated those electrons. Couldn't the nitrogen have donated those electrons? Couldn't these electrons have gone in and gone out like that? That would be showing a resonance structure. And sorry, Mr. Bear is going to have to disappear here for a second. And we could have shown the resonance contributor. And you might wonder, well, why? Why is the resonance contributor worth noting? Whoa. Mr. Bear's coming back. Nitrogen. This might be a bad structure, but what this gives us information about is that we could now potentially see some sites of reactivity. If we're looking back and forth between these, the black one is clearly the better structure, but that red structure is half decent. We're actually having the oxygen hold the electrons, which is actually better than the nitrogen, than having the electrons sitting on the nitrogen. So what we could foresee is potentially these electrons coming in and causing that pi bond to break. But a negative oxygen isn't all that great. So instead of having those electrons come in right away, let's go through and say, take advantage of the acid that is still floating around in solution. Those electrons can come out. Oh man, I am definitely running out of space on this. And I'm hopefully being consistent with where that benzene ring electrons are, but who knows, because I can't see it very well. Hydrogen, positive, there's that lone pair. These electrons can come in. We can break that pi bond. This is ultimately a resonance contributor. But this becomes neat for us because we're now starting to get closer to that something. Okay? And we'll look at the meaning of that something here in a second. We would have a positive nitrogen in the bottom. Again, not particularly stable. So this can be solvent mediated again. Pick up that. Okay? And we could have another HBr. So note we're doing two reactions at the same time. Shuttle, shuttle. And we would end with, there's our benzene ring. There's the nitrogen. The hydrogen's been removed. I now have the 1,2 triple bond to nitrogen, and then I lost water. So what I've got is that structure. That nitrogen is positively charged, and we might think, well, that's not particularly great, but we've got resonance bouncing back and forth to help kind of stabilize that positive nitrogen. Does this satisfy what we've got in our red box? Right? Well, we have a positive nitrogen. We said we wanted a positive carbon. Right? So let's hold off on looking at the positive aspect and let's consider the leaving group. Is this a decent leaving group? Well, nitrogen doesn't want to be positive. If it took those electrons, what would we form? Well, we would have the triple bond between two nitrogens. The nitrogen's no longer connected to the ring. And I would have, holy monkeys, a positive carbon. Well, all well and good. Is N2 a stable leaving group? Well, N2 is gas. That's nitrogen gas. So as a gas, it just bubbles out a solution. Is it stable? Well, our atmosphere is what, 70%, 80% nitrogen? And we aren't dying from nitrogen. If anything, we're dying from the oxygen that's present. We're also living because of the oxygen too, but that oxygen is keeping us in a balanced state between life and death. The nitrogen is really doing nothing. The nitrogen is inert. It doesn't react with anything. So that is a phenomenal leaving group. Okay? The carbocation that would form, hopefully most of you are screaming, but, you can't form. You're right. We cannot form this, which means that step does not happen. Right? Which means at the end of step 1, we end with that goofy looking compound. Okay, so let's draw that in there. And when we delete everything, you'll see it appear again. We would end with this triple bond structure, right? With the positive charge in that nitrogen. That's where step 1 ends. And that structure is actually relatively stable because the carbocation on the benzene ring can't form, right? So if it can't form, then how would we possibly get a reaction to happen? This is why we've got the copper in all of those, or nearly all of those Sandmeyer reactions. The copper catalyzes the reaction, facilitating the leaving group of nitrogen gas and kind of stabilizing that carbocation for long enough that the bromide can then react. Okay? Really neat reaction overall. Like I said, I think it's cool. At least I think it's cool to get up to that benzene diazonium ion. Right? That is the product of that step 1. I tried to offset it so you could see it a little bit better. Right? And then that step 2 can be a myriad of different reagents. Some of them are using copper and some of them aren't, and a lot of that depends on what the other atoms present are. For instance, Ki, iodine is very, very large and can help stabilize some of those crazy intermediates due to its polarizability. The HBF4, you're looking at boron with its goofy chemistry, and probably more importantly, the hydrogen, the boron is probably going to be your trigger there to help stabilize those intermediates so that we can shuttle F- into the reaction. Note that one also requires heat, probably because it's challenging to get that carbocation to form. Okay? And then the last one, the H3PO2, I think the phosphorus being the large atom is what's stabilizing and catalyzing that reaction. So, benzene diazonium ion, right? If you see NaNO2, you're forming this crazy ion, okay? It's just happening. Right? This is where I would argue you should memorize it. This would be one of those things that memorization is probably going to be useful just because there's a lot going on within it. And so it makes sense to actually spend some time to actually do that. Okay? The secondary reagents, I wouldn't bother to memorize. What I would bother to memorize is what I talked about, is that when we see that NaNO2, we know we're going to follow it up with a secondary reaction, and the negative thing in that secondary reaction is the thing that's going to substitute on. Right? That's how I would memorize it. Yes, there's an exception to that. There almost always is, but I could memorize that specific reaction, and then the negative thing is what reacts. Okay? And that would cover my bases and allow me to get that one down pretty well. Okay? With that, we are done with the weird secondary reactions. So 3 cheers for Mr. Bear for subbing in for us. That was very kind of him. And hopefully you have a good rest of the day. And we will attempt to get this video stopped.